Hello, everyone. So this is the video for chapter 5, lecture 2, basically finishing chapter 5 today. So remember last time we went over molarity, right? And then we did solution stoichiometry, then we did precipitation reactions where we wrote molecular, complete ionic, and net ionic equations. So we'll continue here to acid-base reactions. So remember that precipitation reactions are double displacement reactions. Acid-base reactions are as well. Okay. Um, so what does that mean? You guys already know what an acid, how to spot an acid, right? It starts with H, right, which is the proton, H plus, and then followed by, an anion, either a monatomic anion, which is a binary acid, or a polyatomic ion, and those are called oxoacids, right? So acid-base reactions is when an acid reacts with a base to form water and a salt. So basically, it's called a neutralization reaction because the acid and the base cancel out. Okay. Now, bases are really easy to spot too. They are hydroxides. Okay, so anything hydroxide is considered a base. Okay, so you guys may have heard of sodium hydroxide, right? That's a very common base, but you also can have potassium hydroxide, lithium hydroxide. All of those are bases as well. Okay, so when bases and acid react, right, they cancel each other out and they make neutral water and then the corresponding salt, right? A corresponding ionic compound. So that's why it's called neutralization, because water is formed. Okay? So gas evolution reactions, this is, not necessarily a separate class, but it's just when any reaction produces a gas. And so a lot of acid-base reactions are also gas evolution reactions as well. Okay. So that's all that is. Okay. So let's remind ourselves, right? What is an acid and then what's a base? So the Arrhenius definition of an acid, and Arrhenius is basically the grandfather of acid-base chemistry. Um, and he first defined an acid as any substance that produces H plus in water, right, in an aqueous solution. So, something like HCl, okay, and you can tell that this is an acid, right? It leads with H, um, produces H plus, right, in water, and Cl minus. So it looks very ionic, doesn't it? A cation and an anion, right? So acids, you can kind of think of them as ionic because the proton is charged, right? It's positively charged. Um, so now the proton doesn't just stay there by itself. It's quite reactive. So it will get picked up by water. It actually binds to water to form what we call the hydronium ion, right? H3O plus. And this is one of your polyatomics that you should know too, right? So a hydronium ion is just basically an H plus with a water attached to it, right? So there are some acids, so HCl, right? We call this a monoprotic acid because it only has one proton, right? Remember H plus is called proton. So it's a monoprotic acid because it can only release one proton. However, you have polyprotic acids as well, and these contain more than one ionizable proton, and they get released sequentially, right? So something like H2SO4, right? H2SO4 has two protons that can be released, right? And why is it H2SO4? Well, SO4 is 2 minus. Remember, that's sulfate anion. And so you need two protons to balance it out, right? So that's why we call them polyprotic acids. So they have multiple protons that can get released, okay? So again, right? Arrhenius definition says an acid is going to produce an H plus in solution. Okay, so then what is a base? Arrhenius defined a base as any substance that has OH minus ions that can produce OH minus ions. And those are hydroxides, right? So as I mentioned, if you see a hydroxide of any sort, it's going to be a base, right? So sodium hydroxide and OH minus, right? And Na plus comes together. So it will dissociate into Na plus and OH minus. Okay, so when an acid and a base comes together, we call these neutralization reactions. Okay, so let's take a look at this first one here. We have HNO3 aqueous, right? Two of those, plus CaOH2, that's calcium hydroxide aqueous, to form calcium nitrate aqueous and to water. It's a balanced equation, right? So notice how that works. Your acid here is nitric acid, and so the proton is H plus, right? And calcium hydroxide has OH minus in it. So think about it, and the H plus and then the OH minus makes what? H2O, right? H plus and OH minus. And then what's the other couple? Calcium and nitrate. So do you guys see how this is a double displacement reaction, just like a precipitation reaction, right? It swaps partners, right? So the cation here goes with a new anion, and then this cation, Ca2 plus, goes with the new anion nitrate, right? To get calcium nitrate. So the mechanics is the same, which means you guys should be able to predict the products of acid-base neutralization reactions now as well, right? So you always do the double displacement first, and then you balance the equation, right? And what you'll find is when you write the complete ionic equation and then the net ionic equation, the net ionic equation will always be the same. It's the proton and the hydroxide coming together to make water liquid. Okay, that is the net ionic equation, right? And then the salt will just, be whatever salt that you had started with, right? So here's another example, right? You have HCl, that's hydrochloric acid, and sodium hydroxide, that's your base. And what happens? The proton, the H plus, goes with the OH minus to form water, which is liquid, right? And then what's left over? The sodium is going to go with the chloride. And since sodium is plus and chloride is minus, it's just 1-to-1, right? Sodium chloride aqueous, right? And subsequently, like accidentally, the equation's already balanced here, right? And so we're good. Okay. So here's just an illustration of this neutralization reaction between hydrochloric acid and sodium hydroxide. Notice that they are both aqueous, right, to begin with. So they're in their separate test tubes here. Here's the HCl, here's the NaOH, right? When they are poured together, they form water and sodium chloride. So what's happened here? Well, why is it called neutralization reaction? Well, would you drink hydrochloric acid? No, you can't, right? It would damage you badly. And you would not drink sodium hydroxide either, right? You would not just go like that. However, if you put them together, right, now you can drink the products. It's totally fine. You drink this every day, right? Salt water. Okay. So we know a reaction has happened, right? Because the acid's no longer acid, the base is no longer there either, right? It has neutralized, they cancel each other out. And basically you just have water left, right? And the corresponding salt. All right, so on this slide here, it lists some common acids and bases for you guys. Notice, they all the acids, they start with H, right? These are the strong ones here, and then the weak ones are in pink, okay? The base, notice, they all end in hydroxide, right? So that's how you're gonna spot it, right? That's how you're gonna spot it. So now you know two reactions, right? You know precipitation reactions, acid-base reactions. They're both double displacement, right? But how are you gonna tell between one or the other? Well, look for the H in front, right? And look for a hydroxide, then you know it's an acid-base reaction. If you just have a normal ionic compound with another ionic compound, then most likely that's gonna be a precipitation reaction, right? So always look at your compound first and try to identify what it is, right? Classify it first. Oh, that's an ionic compound. Okay. Oh, and now it's going with another ionic compound. So it's probably precipitation reaction. Oh, but here, you have H in front. Oh, so that's an acid. Okay. Are we reacting with a base? Is there an OH there? Is there a hydroxide? Oh, there is. Okay. So then it's a neutralization reaction, right? All right, so let's switch to the board and we're gonna practice some more with predicting acid base products. It's just again, right? Double displacement, but let's practice, okay? So acid base neutralization reactions. They will always form water and salt. Okay, that's the mark of a neutralization reaction, right? That's why it's called that. So let's do a couple examples here. We have, let's do hydrochloric acid and barium hydroxide. So hydrochloric acid, aqueous, right? You guys know the name now too, right? Hydrochloric acid, you should be able to generate that. And barium hydroxide, you should generate that too. Barium is 2 plus, hydroxide is minus. So BaOH2. Okay. And now, remember, it's double displacement, right? We know this is plus and this is minus. And if this is helpful to you, write the charges on top, okay? Just as like a bookkeeping thing. Barium is in group 2A, so we know it's 2 plus. Okay? Each hydroxide is negative, right? That's why we need 2 of them, right? But now that's going to help us, right? So the H plus is going to go with the OH minus, right? They're going to swap partners. Of course, the H plus can't go with barium, right? Because cations are not, right? They're both the same charge. They repel each other. So the plus must go with the minus. What's H plus and OH minus? Water. And what state is water? Liquid. Okay. Plus, barium is going to go with chloride. But since chloride is only negatively charged, like 1 minus, right? And barium is 2 plus. How many chlorides do we need? 2. So it's BaCl2. Okay. Then we look that up on our solubility chart, right? Remember, like anytime you had ionic compounds now, you can look up on your solubility chart so that you can write the state. And you'll find that it is soluble. So remember, we're going to write aqueous. Okay. All right. So that's the first step, right? It's just predicting the products. And then after that, we got to balance the equation. Okay. So put your hand on the most complex. It's looking like this one. Okay. My bariums are balanced. I have 4 hydrogens on this side, right? 2, oh, 3 actually. Okay. Let's do the oxygen first then. 2 oxygens on this side. There's only 1 oxygen here, so I'm going to put a 2 there. Okay. And so now I have to balance my hydrogens, right? On the left side, I have 3 hydrogens. On the right side, I have 4. So how do I get 4 hydrogens on the left side? Well, let's just put a 2 there. So I get 2 hydrogens here and 2 hydrogens there. And now also balance my chlorides, right? 2 chlorides on each side. Okay. All right. So this we call the molecular, right? Equation. Let's practice writing our complete ionic. Okay, so remember, y'all, for complete ionic, anytime you see AQ, I'm gonna split it apart, right? I have 2HCl here, so I'm gonna write 2H plus aqueous plus 2Cl minus aqueous plus barium is 2 plus. See, it's kind of useful to write the charges on top, so you just have it right there. Okay, just figure it out and then write it down. And then, okay, pay attention to the coefficients, right? And also the subscripts. That's telling you there are 2 units of hydroxide, right? So that's 2 units of hydroxide. Okay. Those 2. Do we split this up, guys? No, right? Because liquid does not get split up. Only aqueous gets split up, right? And then, so aqueous, we split that up. Ba, we already know is 2 plus, right? Aqueous. And we had chlorides charge up earlier, 2Cl minus. And then for the net ionic, right? All I need to do is cancel things that occur on both sides. Okay, and barium. Chloride and barium. So what do I have left? 2H plus aqueous plus 2OH minus aqueous goes to 2H2O liquid. But notice these two can just get divided, right? Divide everybody by 2, so you end up with this. Okay. All right. And then you just need to put what the spectator ions are. It's the ones that you cross out, Ba2 plus and Cl minus. Okay. Makes sense, right? Okay, so you see how it looks just like last lecture when we did precipitation reactions, right? Doing molecular and ionic. Okay. Let's do another example. This time, let's do lithium hydroxide aqueous plus sulfuric acid, H2SO4 aqueous. Okay, goes to, okay, predicting the products, right? Remember, it's just swapping the partners, okay? Get the charges first. I think this is really gonna be key to making this a lot easier on you. Just get the charges first. What's lithium's charge? It's in group 1A, so it's a plus, right? Write that on top. What is hydroxide's charge? It's gonna be negative, right? You know your polyatomics. What is H charge? Well, it's a proton, right? So each H is a plus, right? We know that sulfate is 2 minus. We know our polyatomics, okay? So now, see, doesn't that just look easier to do? We got a plus here and we got a 2 minus. That means I need 2 lithiums, right? So Li2 SO4. Now I got to look at my chart, right, to see if that is soluble or not. Okay, so it's a sulfate. We're going to look, okay, sulfates are generally soluble, and there are no exceptions for lithium. So, well, aqueous. Then plus, what's the other product? Well, the OH minus is going to go into the H plus, right? H plus and OH minus. And so that's going to make H2O. And we know that's a liquid. Okay. So as you can see, right? Always water and a salt. That's what a neutralization reaction makes, right? Water plus whatever corresponding salt. Okay. Next step, balance it, right? Okay. Put my finger on here, most complex. Balance the lithium first. I'm going to put a 2 in front of there. The sulfates balance. Okay, so I'll go over here. I need 2 oxygens. That's just 1 oxygen, so I'll put a 2 here. That's 4 hydrogens, and 2 and 2, 4 hydrogens on each side. Okay. All right, so now that that's balanced, I know that that's called a molecular equation, right? That's called a molecular equation. What if we want the complete ionic? Split up the aqueous, right? So 2 Li plus aqueous plus 2 OH minus aqueous plus. This gets split up too, right? And that's 2 protons there. 2H plus aqueous plus SO4, 2 minus aqueous goes to, this is aqueous, so we split it up as well. 2 Li plus aqueous plus SO4, 2 minus aqueous plus 2. Okay. And now we cancel things out that are the same on both sides. So what do we get? Sulfate is gone. Lithium is gone. And we have 2 for the net ionic, right? 2 OH minus plus 2H plus goes to 2 waters again. Okay. And see these 2's in front just get canceled, right? Or yeah, we just simplify it down, right? So OH minus plus H plus is water. Notice this net ionic equation is the same as the last one, right? So for all acid-base reaction, and the last one, right? Same. So all acid-base neutralization reactions have the same net ionic equation, right? Remember, that wasn't true for precipitation, but for acid-base it is. Okay, so spectator ions SO4 2 minus, and Li plus. Okay. All right. So you guys go practice that, right? It's the same mechanics as the precipitation reaction, but the only thing here is, you know, you got to learn. I think you guys already know how to spot an acid, but now, right? The new thing is spotting a base. So if you see them together, you know it's an acid-base neutralization reaction. Okay. But if you just do double displacement, right, you'll figure it out. Oh, you're like, oh, it makes water, right? It has to go to make water, right? OH minus and H plus. Okay. So just do the double displacement, and you should be fine. All right, so let's move on to acid-base titrations. Okay, so this is titration is a lab technique, and you guys are going to be doing this pretty soon here in lab. So what titrations are? It's a technique that uses a known to figure out an unknown. Okay, so you're going to use a substance that we know the concentration of to figure out the concentration of the unknown solution. Okay. So the equivalence point, okay, that's where the point where all of the acid has neutralized the base. Okay, so that we call that the equivalence point. And we can use an indicator to see where the equivalence point is, and that's going to help us figure out, okay, what is my unknown concentration? Okay, so this is how it works. Here's a diagram. Okay, so let's say at the beginning of that titration, you only have acid in your flask here. Now you see that H plus, okay? And then you'll have a burette. This instrument here is called a burette. This thing here is called a stopcock. Okay, that's what it just swings around so that you can release the hydroxide, the base here. Okay, so inside this burette, it's gonna be base, and it's usually the base that has a known concentration, and you don't know what the concentration of the acid is. Okay, but since you know that it's a one-to-one, right, stoichiometry, you see one base, right, one hydroxide will react with one acid, H plus, to form water. Okay, so basically the way I like to say it is one base is going to kill one acid, right? So it's a one-to-one ratio. So if you know the concentration of the base and you know how much volume you drop in to get to the equivalence point, then you also know how much acid you had in the flask, right? Because it's one-to-one, right? So if you know the volume of base that's added, you can calculate the number of moles of base that's used, and that must be the same as the number of moles of acid that's in the flask, right? Just by deduction, right? Simple logic there. And then once you know the moles of acid, you just divide by the original volume of the acid to get the concentration of the acid, right? Remember, concentration is measured in molarity, and that's moles over liter, right? So that's, you know, all there is to it. It's actually a quite simple method to figure out the unknown concentration. Okay? Now, the indicator is added before you do the titration so that when it reaches the equivalence point, the indicator will turn a certain color. So in this diagram, since it's pink, it must be phenolphthalein. Phenolphthalein is used to indicate when you have a pH of 7. Okay, so when you have a pH of 7, it will turn pink. Okay, pretty cool. So that means if it's not a pH 7, it stays colorless. And so that's how you know that at the equivalence point is when your titration's done, right? Because everything has gotten turned into water. And what's the pH of water? Well, it's neutral, so it's going to be 7. Okay. Okay, so let's do a titration problem together here. So let's read the problem first, and I'm going to show you guys how to do the calculations, okay? It says the titration of 10.00 mils of HCl solution of unknown concentration requires 12.54 milliliter of a 0.100 molar sodium hydroxide solution to reach the equivalence point. What is the concentration of the unknown HCl solution in molar? Okay. All right, so I'm going to try, we're going to draw a diagram first. So you guys can see what this is about, right? And I'll show you the the calculation. So let's go back to the board. Okay, so we have our flask. Okay, sorry, I'm a terrible artist, but that's a flask, okay? And it says what? How much is in the flask? 10 milliliters of HCl. So we know the volume here, and we know HCl is in, but we don't know the molarity, right? That's what we have to find. Okay, and then it also says the base solution, it requires 12.54 milliliters of a 0.1 molar NaOH solution. So we know the molarity of NaOH, right? It says 0.1 molar. And it's going to be in this burette. Okay, and stop copy, right? So it says we're going to use 12.54 milliliters, let's say. That's the mark, right? That's how much we use. So on the burette, it's like a graduate cylinder. It has these readings. So you can actually, see how much volume that you dropped into there. Okay. And we know it is 0.100 molar sodium hydroxide. Okay, so that's our known. And the question is, what is the concentration of HCl? Okay. All right. Okay, so we know that we use this much, right? This volume of base. We also know its molarity. So remember, with a volume and a molarity, you can figure out moles. I remember a roadmap. Okay. So anytime you see a volume that's tied to a molarity, you can get moles out of that, right? That's how you need to think. Okay. And what you do is you start with the volume. Right? Don't start with the molarity. Okay. Start with the volume. So 12.54 milliliters. But remember what molarity is, what molar is. I should rewrite that too. Remember in last lecture, I told you anytime you see big M, rewrite it as moles over liter. Okay. And moles of what? Sodium hydroxide. Okay. So now I know that I need to change my milliliter to liter because my molarity is in that unit, right? So I'm going to divide by 1,000. 1 liter on top, right? And now I want moles out, right? Moles of NaOH. Okay. So what is that? 0.100 moles NaOH should go on top. And 1 liter on bottom. Okay. All right. So now at this point, I know I need to get from moles of NaOH to something HCl, right? Because right now I just have moles of NaOH. Okay. So I need to basically know the mole-to-mole ratio, don't I? Remember the roadmap? If I want to go from mole A to mole B, I need to know the mole-to-mole ratio, which means I need the balance equation. Okay, so we got to write that. In fact, we should have written that first. Okay, we should make a habit to actually write that first. So what did we react? HCl and NaOH. HCl aqueous plus NaOH aqueous. Those two. Okay. And you guys know how to predict products now, right? H plus and OH minus is come together to make water. Plus Na is going to come together with Cl, right? Na is plus, Cl is minus to make NaCl aqueous. Okay. And then we try to balance the equation, right? Let's see. We got 2 hydrogens. That's 2 hydrogens on the left side, 1 oxygen on each side, 1 sodium, 1 fluoride. Oh, it just so happens to balance. Beautiful. So now you can see the ratio, right? 1 base, 1 acid, 1 to 1. So here we go. We applied a mole-to-mole ratio, right? 1 mole of HCl on top and 1 mole of NaOH on bottom. Okay. And then one more step, right? We want the concentration of HCl in molarity. Remember what molarity is? Moles over liters. So right now we have moles. All we have to do is divide by liters, right? And how much HCl do we have to begin with? 10 milliliters, which we can convert to liters. Okay. So that goes here, right? 0.01 liters. And here it's just a placeholder 1, right? So as you can see, now we have moles over liter as our unit. And then we just calculate, right? And it's 4 sig figs from these numbers. So 0.1254 liters. Or sorry, molar of HCl, right? Yeah. Okay. Okay, so all I did here, right? I just contracted it again. Remember, molar is a contracted unit of mole over, right? So it's just more convenient to write that, but you could have written moles over liter HCl as well. Doesn't matter, right? But remember, that's what big M is, right? So that's how you do a titration calculation, right? You guys should save that because you're gonna be doing that in the lab. All right. All right, so let's move on. So there are these gas evolution reactions. I'm not gonna test on these. You should learn it to do the homework, but I'm not gonna test you on it. So we're gonna move on to the last type of reaction that you're learning. So look, you've already learned precipitation reactions, acid-base neutralization reactions, right? Both of those are double displacement. And then this third one is called oxidation reduction reactions. Okay. Or I like to refer to as redox, right? Reduction oxidation, just for short, redox reactions. Okay. So redox reactions are oftentimes quite easy to spot because it will involve like a metal or something in its elemental state, right? Like an element turning into a compound. Okay. Remember those terms, right? Iron, the element, oxygen, the element, turns into iron 3 oxide, which is rust, right? It's the rusting of iron, this reaction, okay? So this is called a redox reaction. It involves movement of electrons, okay? That's what redox means. Okay, and then combustion reactions, those are redox reactions as well, okay? And here's this one, right? This is also considered combustion because you have O2, right? You don't form carbon dioxide and water because you don't have carbon, right? But you do form just water here. So it does technically is also combustion. So the formation of water. But you can also see, right? These are elementals getting turned into a compound. So anytime that you have elements turning into a compound, it's going to be redox. Here too, this is redox as well because you have metal, non-metal in their elemental state. And what is it forming? An ionic compound, right? And you have electron transfer here, right? Because the sodium was neutral and now it's become plus. So the sodium lost its electron, the chlorine gains it, right? So you have this movement of electron. It's called redox reactions. Okay. Okay, so so far we've made it very black and white as far as like you have ionic compound or you have covalent compound, right? Ionic compound is complete transfer of electrons, right? And in covalent, right, you don't have that, right? Well, the reality is, everything falls on a spectrum, okay? So even in covalent compounds, such as HCl, you do have some transfer of electron. You don't get a complete gain or loss, but you have a transfer of electron. Okay. So for example, in HCl, the chlorine is actually more dominant at drawing electron density towards itself. And so that's why we give it a delta minus. Delta means partial. So it's partially negative because the electron density lies more on the chlorine than on the hydrogen. So the hydrogen feels deprived of electrons. So that's why it gets a delta positive on it. Okay. So here you do have sort of an electron density transfer. Okay. Compared to, say, the reactants, H2 and Cl2, they share the electrons equally, right? The electrons were equally shared. But in HCl, it's, uneven sharing, right? So it's not a complete electron transfer, but it's a partial electron transfer, okay? And so that's why we don't consider, HCl as an ionic compound. Although in water, it kind of acts that way, right? Because it's like H plus and Cl minus, right? So that's why it's kind of ambiguous, right? It's not really an ionic compound, but it's also not purely covalent. It's somewhere in between. Right? And so in the next part now, when we're learning oxidation states, this is like a bookkeeping system that allows us to figure out where the electron density mostly lies. And then we kind of winner takes all kind of thing, right? So instead of having to worry about, delta minus, delta plus, when we look at oxidation state, which is like, okay, chlorine, you can have the whole electron. So chlorine has a -1 oxidation state and hydrogen always gets a +1, okay? So that's the system that we're gonna learn now is oxidation states, okay? Before we do that though, you guys need to know the term. What is oxidation? What's reduction? I'm going to teach the way that I learned it, which is Leo says GER. I think it's easy to remember and it's kind of cute, right? So lose electron oxidation, right? That's for Leo. And then GER, gain electron reduction, right? Leo says GER. So when something loses the electron, you say that it is oxidized. And when something gains the electron, you say that it is reduced. Okay, so let's look at the formation of table salt, right? From the elements. We've seen this reaction quite a bit, right? But now we're going to really analyze where the electron's going. So you have sodium solid, right? That's neutral. And you have chlorine gas, Cl2 gas. Both are in the elemental state, so neutral, right? They got all their electrons. And then they form table salt. So in table salt, the sodium is plus and the Cl is minus. So what has happened? Well, it looks like the sodium lost its electron and the chlorine gained one to be Cl minus, right? So there's obviously an electron transfer from the sodium to the chlorine, right? So since the sodium lost its electron, we say that the sodium is oxidized, right? That's the oxidation reaction, okay? Notice how it's written too, right? Na neutral goes to Na plus and plus one electron, right? Because it lost an electron. And then for chlorine, it gained one, right? So Cl2 goes plus 2 electron goes to 2 Cl minus, okay? So notice the electrons coming on the left side is a reduction, and the electrons coming on the right side is an oxidation, right? Because here you lose electron, and here you plus, right? Plus 2 electrons, so you get reduced. All right, so we say, the chlorine got reduced, and sodium got oxidized. Okay, so now let's move on to that oxidation states, right? As I was talking to you guys about. For reactions that are not like ionic, oxidation states just make it really much simpler to figure out where the electron density lies, right? So it's like a winner takes all kind of thing, right? So remember with the HCl case, Cl gets a -1 oxidation state and H gets a +1, right? Just because Cl has more electron density on it than hydrogen, okay? So it's just a bookkeeping method, okay? It's not an actual charge, right? Because if we have covalent compounds, we can still talk about oxidation states, but obviously they're not charged, right? It's just a way for us to figure out where the electron density mostly lies, okay? So even though it looks like it, oxidation states are not charges. And that's why for oxidation states, you guys should say sign before number, right? That's why I've been anal about that, right? If it's a charge of, the charge is 2 minus, right? You say the number first and then the sign. But oxidation state, you say -2, okay? So that we can keep track of real charges and then just oxidation states, okay? All right, so let's go into the rules for assigning oxidation states. Okay. Rule 1 is pretty easy, and it makes sense too. So rule 1 says free elements have an oxidation state of 0, right? Well, that makes sense, right? Free elements have all of their electrons. They're not ionized, so they gotta be neutral. So anytime you see an element, like an atom by itself, right? Just one type of atom in the compound, right? Or not compound, right? Just an atom, or a diatomic element, right? Then you know its oxidation state has to be 0. Okay. Number 2, monatomic ions. What does that mean? One atom. Single atom ions have an oxidation state equal to their charge. So if we have an Na plus, right, like in NaCl, Na is plus. So the oxidation state of sodium is +1 because its charge is 1 plus. You see that? So it matches up to its charge. Chloride is 1 minus charge. So it'll get an oxidation state of -1. Yeah. So that rule is pretty easy too, right? And then the third rule, the sum of the oxidation states of all the atoms in a compound must equal to 0. Right? So in NaCl, for example, Na has an oxidation state of +1. Cl has an oxidation state of -1. +1 and -1 is 0. Okay. So this rule is like similar to charges too, right? Charges and compounds also have to be 0. Okay. So it's kind of nice. It's even though you're learning something new, it has ties to something you already know. So it's the same logic, right? Which is nice. Rule 3b, the sum of the oxidation states of all the atoms in polyatomic ion equals the charge on the ion. Okay, so for example, nitrate, right? Nitrate has an overall charge of negative. Okay. So that means the oxidation state of nitrogen and all the 3 oxygen have to add up to -1, right? And indeed it does, because oxygen has -2 as the oxidation state, and nitrogen has +5. So oxygen -2 times 3 is -6. -6 plus 5 is -1. All right. Rule 4a. Group 1 metals have an oxidation state of +1 in all of their compounds. So Na is +1, right? Because Na is in group 1a. Makes it easy. Same as charge, right? So here it's similar to charge too. Group 1a is always 1 plus, so it's always going to be +1. Group 2 metals, group 2a metals, oxidation state is always +2. Very similar to charge, right? What is the charge of group 2a? 2 plus. Okay, so therefore oxidation state +2. Just like in magnesium chloride, right? Mg is never anything but +2 for oxidation state, which is nice, right? Doesn't change on you. Now, rule 5, okay? Rule 5 gives us a table for a priority for nonmetals. Okay, so far we've only been talking about metals, right? So metals definitely take precedence. It's higher on the priority list, as in you assign it first, right? Because it never changes. So it's kind of becomes your reference point, your anchor, right? So you assign the oxidation state of the metal first and then the nonmetals, okay? But the nonmetals themselves have a priority as well. So let's look at the priority. Fluorine gets assigned before hydrogen. Hydrogen gets assigned before oxygen. And then it goes group 7A, group 6A, and group 5A. Okay. And what are their oxidation states? Well, fluorine will get an oxidation state of -1. Why, you ask? Well, look at your periodic table. What group is fluorine in? 7A, right? So charge would have been 1 minus, oxidation state -1, right? Hydrogen. Why does hydrogen get an oxidation state of +1? Well, it's in group 1A, right? Oxygen gets an oxidation state of -2. Why? Oxygen's in group 6A, right? And then group 7A, of course, we'll get oxidation state of -1, group 6A, -2, and group 5A, -3. Okay. So again, these are like easy to remember. You kind of know it already. It's very, it's kind of mirroring the charges a bit, right? Okay. So let's keep those priorities in mind. And then we're going to do these problems together. And switch over to the board. Let me write down the priority list first. And then we're going to use it, right, to assign oxidation states. Priority list. So group 1A and 2A first, and then it goes fluorine, hydrogen, oxygen, and then group 7A, group 6A, and group 5A. Okay. Okay, so the first one up is Cl2. All right, what should that be, everybody? Wait, it's not a compound, huh? It's just there's only one type of atom in here. That's an element. All elements get what? 0 oxidation state. Okay, and you should write it above the atom just like I do it. Okay, so do it like exactly how I do it. How about Na plus? Oh, this is the rule. If it's a monatomic ion, it's going to have the same oxidation state as the charge. The charge is 1 plus, so it's going to get a +1, right? CKF. Okay, now when you have multiple atoms in the compound, you can use your priority list, right? Which one would you assign first? Remember, metals in group 1A and 2A take precedence, right? So assign those first. Okay, K is in group 1A, so it's going to get a +1, okay? And then since this is +1, this has to be -1, right? And that fits with fluoride, right? Being -1, right? Let's look at D. CO2. All right, so again, we got 2 atoms with a carbon and oxygen. Which one should we assign first? Well, let's look at our priority list. Carbon's not even on here, so we gotta assign oxygen first, right? Oxygen gets what? A -2. How do you know that? Look on your periodic table, right? Group 6A is oxygen. So it's gonna be -2. So -2 times 2 is -4. And remember, it has to be neutral. So carbon has to be a +4 oxidation state. And +4 -4. Okay. Let's look at E. SO4 2-. All right, remember that rule? Now, all the oxidation states of the atoms must add up to the same as the charge, okay? Again, between sulfur and oxygen, which one takes priority? It's gonna be oxygen, right? Sulfur is not on here. Well, sulfur is in group 6A, which is lower priority, right? So oxygen is -2. So now we have -2 times 4 is -8, okay? -8 plus what is 2 minus? Think about that. Sulfur has to be +6, right? Because a 6 and a -8 gives you a 2 minus, right? All right, F, it's K2O2. Between potassium and oxygen, guys, which one are you going to assign first? Well, let's look at the list, right? It's group 1A, potassium, so it's going to be +1, right? And now you assign oxygen. Well, potassium +1, oxygen, what does oxygen have to be to make it all neutral? +1 times 2 is +2. So over 2 oxygen, it has to be -2, right? So each oxygen has to be -1. Right? So Do you see how in E and F, oxygen has different oxidation state? In E, oxygen has -2. In F, oxygen has -1. But you don't have to memorize that if you use the priority list. It'll just work itself out, right? And so that's why you have the priority list and you should use it. Okay? All right, let's keep going. The practice 5.13 here. Cr, chromium. Wait, it's only one type of atom. It's the element. So it's going to be 0 for the oxidation state. B, chromium 3 plus. Okay. Oh, it's a monatomic ion. So it's going to have the same oxidation state as a charge. 3 plus, so +3. C, CCO4. Okay, so between carbon and chlorine, guys, which one are we going to assign first? Let's look at that priority list. Carbon's not even on here, right? Carbon's in group 4A. So it's chlorine's in group 7A. We'll do that one first. Remember group 7A, we have -1, right? So now we have 4 chlorine, so -1 times 4 is -4. And carbon is, that has to be +4. Okay. Let's do D. SR, BR2. All right, between SR and BR, which one are we going to assign first? Let's look at the metals in group 1A or 2A. Yep, strontium is in group 2A. So therefore, strontium will get +2. Okay. And since this needs to be neutral, each bromide has to be -1. Right? Strontium bromide. Let's look at SO3. All right. Between sulfur and oxygen, everybody, which one are we going to assign first? Oh, sulfur is in group 6A. However, oxygen's above sulfur, right? So oxygen gets -2, right? Because it's in group 6A. -2 times 3 is -6. So sulfur has to be what? +6. Right, F. Oh, we did nitrate already. Let's do something else. Let's do the phosphates. Okay. All right, between phosphorus and oxygen, guys, which one are we gonna assign first? Looks like oxygen, right? Because phosphorus is in group 5A. So -2 for oxygen. -2 times 4 is -8. What does phosphorus have to be to get to have a -3 left over? Well, it has to be a +5. Okay. -8 plus 5 give you -3. Okay. So is that clear, everybody? Doing the oxidation state? Okay. All right. Let's go back to the slides. All right. So now that you guys know how to assign oxidation states, right? We're gonna start assigning, to a reaction, right? Which compound is oxidized, which one is reduced, and what's the oxidizing agent, and which one is the reducing agent. Okay, so let's look at this problem here, right? You have carbon plus 2 sulfur goes to CS2. The first thing you do when you see a reaction like this, and it'll ask you, is this a redox reaction? You have to assign oxidation state first, right? So that's why we just learned that. So assign oxidation states to all of the atoms. So write a 0 on top of carbon, 0 on sulfur, right? Because these are elementals. And then between carbon and sulfur in CS2, sulfur should be assigned first, right? Because it's in group 6A. So -2. And -2 times 2 is -4. So the carbon has to be +4, right? Now, once you have the oxidation states, what you do is figure out which of the atom changed. Oh, the carbon was 0 and it became +4. So that changed. Let's figure out what happened to carbon. If carbon goes from 0 to +4, right, it became a cation, right, basically. That means it lost electrons, okay? 0 to +4 must mean it lost electrons. So that's oxidation, okay? And then sulfur goes from 0 to -2. So what happened? It gained electrons, right? Became more negative. So basically the increase in oxidation state is an oxidation. A decrease in oxidation state is a reduction. Okay. So we say carbon is oxidized, sulfur is reduced. Okay. Now, the terms reducing agent and oxidizing agent. Sometimes that's confusing, but if you pay attention to the word agent, it makes more sense. Okay, so here's an example. A reducing agent is the agent that reduces somebody else. So therefore, the reducing agent gets oxidized. Okay, you see what I mean, right? It might seem like opposite in terms, right? But it makes sense, right? The reducing agent is the agent that reduces somebody else, so in turn they get oxidized. Okay, so something that is oxidized is called the reducing agent. Now, opposite of that, right? Oxidizing agent is the agent that oxidizes somebody else. So in turn, they must be reduced, right? So if they cause somebody else to oxidize, then they gain the electron. They got reduced. So oxidizing agents get reduced and reducing agents get oxidized. Okay. So going back to the sodium chloride example, right? Sodium was oxidized and the chlorine was reduced, right? So sodium is the reducing agent and Cl2 is the oxidizing agent. Okay. So the oxidizing agent, you want to list the whole thing, right? Not just the atom. You see, when you say who's oxidized and who's reduced, you just list the atom, right? But when it's the agent, you list the whole thing. Okay. All right, let's do this combustion reaction on the board. So we have CH4 gas plus CO2 gas goes to CO2 gas plus H2O gas, right? Combustion. We can balance too. It's going to be two here. And that looks good, right? So our question is this a redox? If yes, determine what is oxidized, reduced, and which are the oxidizing agent and reducing agent. Okay. This down. Okay. So remember, before you can do any of that, you have to assign oxidation states to all atoms, right? That's why we practiced that before. So in CH4, which one are you gonna assign first? Hydrogen, right? +1. So therefore, carbon has to be -4. Okay. And here in oxygen, oh, that's an elemental, right? Just one type of atom, so it's going to be 0. On this side, CO2, between carbon and oxygen, which one are you going to assign? Oxygen first, right? That'll be -2. -2 times 2 is -4. So carbon has to be +4, right? Remember, they have to be neutral, right? -2 times 2 is -4. That has to be +4. Now in water, between hydrogen and oxygen, okay, when you're assigning oxidation state, do not care about the two, okay? Don't care about the coefficients, just looking at the atoms, right? So between hydrogen and oxygen, which one you assign first? Hydrogen. Hydrogen gets a +1, okay? And so that's +1 times 2 is +2. Oxygen has to be -2, okay? So now you look for changes in oxidation number from the left to the right. And we do have changes, don't we? We see that carbon goes from -4 to +4. So we can already answer our first question. Is this a redox reaction? Yes, it is, because you have oxidation state changing. So a -4 to a +4, that's an increase in oxidation state. That means that we have a loss of electron and therefore this is an oxidation. Okay? When you look at oxygen, you see that it goes from 0 to -2. So a drop in oxidation state is a gain of electrons, and so therefore is a reduction. Okay? So what do we say? We say carbon, right? Just the atom of carbon is oxidized. Okay. And so therefore, what kind of agent is carbon? If carbon got oxidized, that means it made somebody else get reduced. So therefore, CH4 is the reducing agent. Okay. See, when I list the agent, I list the whole compound, right? But for whether something's oxidized or reduced, it's just the atom, right? So the carbon itself is oxidized, CH4 is the reducing agent. And here, oxygen is reduced, right? Single oxygen atom is reduced, and O2 is the oxidizing agent. Okay. Right, let's do another one. This time, same question, right? But now it's C2H5OH plus 3O2 gas goes to 2CO2 gas plus 3H2O gas. Okay, so we're gonna balance equation, right? And remember, you don't care about the coefficients, right? Just look at the atoms. Okay, so let's do this one first. We're gonna assign oxidation states to all the atoms. Okay, between carbon, hydrogen, oxygen, which one do you assign first? Remember, hydrogen priority, right? So all the hydrogens gets a +1. And then next priority is oxygen. Remember, oxygen gets a -2. This is in group 6A, right? So what has to be carbon? Let's figure that out. We have 5 times +1. That's 5 plus, right? And another +1, right? So +5 + 1 is +6. +6, but then there's a -2. So that brings it down to a +4. So +4 over 2 carbons. Each carbon has to be negative, right? So +4, 2 carbons have to be -4. So each carbon is -2. Okay. And you can check too to make sure that this is 0. -2 times 2 is -4. Another -2 is -6. And then here, +1 times 5 is +5. And the +1 is +6. Okay. All right, so we got that one. O2 is easy, right? That's just elemental, so it gets a 0. And CO2, we did this earlier, right? Oxygen gets -2. Carbon gets +4. Water we did earlier too. We do hydrogen first, +1. And that's +2, and so oxygen is -2. Okay. All right, now do we have oxidation states change? Oh, I see it. I see carbon changed. Okay, so it went from -2 to +4. It went up in oxidation state, so you have a loss of electron here. So we have oxidation. And then what else changed? See, the hydrogen stays the same. Oxygen changed. It went from 0 to -2. So it went down in oxidation state. We have a gain of electron. We call that reduction. Okay. Okay, so then we say that carbon is oxidized. And therefore C2H5OH is the reducing agent. And then O is reduced. And O2 is the oxidizing agent. Right? Yeah. So definitely, a problem like this will be on exam number 2. Okay, so you want to make sure you're doing good at that. In fact, let's problem is gonna be on the next quiz, right? So quiz number 3. Okay, so make sure you practice plenty of that. Okay, okay, let's do another one. Mg solid. So on the slide, it's problem 5.14. That's what we're doing. Mg solid plus 2H2O liquid goes to MgOH2 aqueous plus H2 gas. All right. Yep, everything looks balanced too. Okay, so again, we're asked, right? Use oxidation states to identify what is being oxidized, which one is being reduced, and also who is the oxidizing and reducing agent. So again, assigning oxidation states first, Mg, right? Just a single atom, just one type of atom, so it's gonna be 0. Now, water, we've done this before, right? We're gonna do hydrogen first, that gets +1, and +1 times 2 is +2, so oxygen has to be -2. Then we go over to this side. Okay. Between magnesium, oxygen, and hydrogen, which one are you gonna do first? Well, that's pretty easy. Magnesium is in group 2A, so we're gonna do that first, right? So magnesium is gonna get a +2. Okay. And now you should recognize that OH is your polyatomic. So write the polyatomic separately out, okay? And really you don't care about the subscript, right? Okay, it'll work itself out. So yeah, remember don't care about coefficient or subscript, just write the polyatomic and remember it has a negative charge. Now do it separately. So you're like, okay, hydrogen should get a +1 because it has higher priority, right? Yeah, so let me write that more clear. +1. And this has to add to oxygen to be negative, so oxygen has to be -2. Okay, so there we go. We worked it out. So oxygen is -2, hydrogen +1. Okay. And then here we have hydrogen gas only one type of atom, right? Its elemental state, it's 0. Okay. And then we analyze which numbers changed. Oh, magnesium or change oxidation numbers, right? Went from 0 to +2. That's an increase in oxidation state, loss of electron, and therefore oxidation. Okay. And then hydrogen went from +1 to 0. It went down in oxidation state, so we have a gain of electron, right? Leo says Ger, we have a reduction. Okay, so now we write it all out. Mg is oxidized, and therefore Mg is the reducing agent, right? And then hydrogen is reduced, and therefore H2O, right? Remember, when you do agent, you write the whole thing. H2O is the oxidizing. Right? Okay. See that every single time, the same steps, right? Assign oxidation states to every atom first, and then see which ones changed, and then list it out, right? Okay, so that's pretty much it. There are more problems for you guys to practice, and I really suggest you do that, right? Because this is definitely going to be on quiz 3, right? So the 5.15, you guys just do, right? There's answers there, and there's even more practice down here, okay? So do that, practice that on your own, and come to me if you have any questions, all right? So that's it for chapter 5. I'll see you guys next time for chapter 6. Bye-bye.